And the established framework measuring the time efficiency was based only on the problem's input size. But there are many algorithms for which running time depends not only on an input size but also on the specifics of a particular input. In other words, the running time of the algorithm is not the same for all instances of an input of size n. Let's take an example to elaborate more on this step. Suppose you have an array of size 10 as input parameter to an algorithm. The question is the running time of this algorithm the same for all instances of this array? Is it the same on all arrays of size 10 even if you change the values of the array elements? If the answer is no, then you have efficiency cases. So what are these cases? If the basic operation is always executed the same number of times for every instance of the input of size n, then we have efficiency that is called every case efficiency. And this occurs if the values of the input parameters do not affect the execution time of the algorithm for every input size. In simple words, input data has no effect on the running time. Consider the following two algorithms. The first algorithm on the left returns the sum of all elements of an array of size n. The second algorithm on the right returns true if the array has a negative integer, otherwise it returns false. Let us consider the first algorithm on the left. The algorithm is using an accumulator that is called sum. In every iteration of the for loop, the current element of the array is added to sum. At the end, the value of sum is returned by the algorithm. Where is the basic operation? The basic operation is the addition at line 4. And since it is repeated in every iteration of the for loop, the number of times this basic operation is executed is equal to the number of iterations of the for loop. Now, since the for loop goes from 0 to n-1 n times, then the number of times the basic operation is executed is also n times. Now, suppose we have an array of fixed size. As an example, an array of size 7. And we run this algorithm on this array. Then how many times the basic operation will be executed? The answer is 7. Because the for loop will go from 0 to 6, 7 times, and the addition operation will be executed 7 times. Now, if we change only the data of this array, and we keep the size fixed, we keep the size equal to 7, and we run the algorithm again on this array, how many times the basic operation will be executed? And again, it will be equal to 7. Why? Because the for loop again will go from 0 to 6, 7 times, and the basic operation, which is the addition, will be executed 7 times. In conclusion, the basic operation is always executed the same number of times for every instance of this array of size 7. In this case, we say that we have every case efficiency. Now let us have a look into the second algorithm. This algorithm is using a for loop that iterates over all elements of the array one by one. In every iteration, it compares the current element of the array ai. If it is negative, then the algorithm immediately stops the for loop and returns it true. Otherwise, if no negative number is found in the array, then the algorithm will exit the for loop and returns false. Now, what is the basic operation? The basic operation is the comparison operation at line 3. But is the algorithm going to execute this basic operation the same number of times for every array of size n? That's what we need to know. If we have an array of size 7, is the number of comparisons will be always the same for every instance of this array? An array of size 7? The answer is no. Now suppose the first element in the array is negative, then we have only one comparison. And if it is the second element, then we have two comparisons. And if no negative exists in the array, then we have n comparisons. So we have cases. We have the best case, which is one comparison when the negative integer is the first element in the array. And we have worst case with n comparisons when the negative integer is at the end of the array or no negative integer exists in the array. In conclusion, in the first algorithm, the basic operation, which is addition at line 4, is always executed n times for every instance of the array A. But in the second algorithm, the basic operation comparison at line 3 is not always executed n times for every instance of the array A. Why? Because the execution of the basic operation not only depends on the input size, but also on specific values of the input instances. From our previous discussion, if the frequency of the basic operation is always the same for every instance of an input of size n, I mean if it is not affected by certain values of the input, then there is only one efficiency, that is called every case efficiency. But if the number of times the basic operation is executed depends not only on the input size, but also on the input values, then we have to consider 3 cases for efficiency. We have to consider worst case, best case, and average case for efficiency. Let us go over these cases one by one. The worst case efficiency of an algorithm is defined as the efficiency when the basic operation is executed the maximum number of times for every possible instance of the input of size n. As an example, by going back to the negative test algorithm, the algorithm makes the maximum number of comparisons when the array has no negative integer or the negative integer is at the end of the array. In this case, the efficiency is called worst case efficiency. Now for the best case efficiency of an algorithm, it is the efficiency when the basic operation is executed the minimum number of times for every possible instance of the input of size n. And again, by going back to the negative test algorithm, the algorithm makes the minimum number of comparisons when the first integer of the array is a negative integer. In this case, the efficiency is called best case efficiency. Finally, the average case efficiency of an algorithm is defined as the average or expected value of the number of times the algorithm executes the basic operation for an input of size n. And to find the average case efficiency, we need to consider all cases between best and worst cases, and in each case we find the number of times the basic operation is executed to get the expected value of the number of times it is executed. To clearly understand the difference between these 3 cases, let us have a look into an example. The example is the sequential search algorithm, and in this algorithm, the element we need to look for in the array is called the key element, or we can call it key for short. So how the algorithm works? The algorithm searches sequentially for a given key that is called k in an array A, and returns the index of the first element in the array that matches the key. Otherwise, it returns -1 if there are no matching elements are found in the array. This is the pseudocode for the sequential search algorithm. The input is the array and the key element k that we need to look for in this array. At line 2, the algorithm iterates over all elements of the array by a for loop from 0 to n-1. In every iteration at line 3, it compares the current element ai if it is equal to the key or not. If it is equal to the key, the algorithm immediately stops the loop and returns the index of this element. And if no element is equal to the key, the algorithm exits the loop and returns -1, indicating that the key is not found in the array. Notice that the basic operation is the key comparison at line 3, and the efficiency of the algorithm is not every case efficiency, because the number of comparisons is not always the same for every possible instance of the array. As an example, if the key is at index 0, I mean if a0 is equal to k, then the algorithm will make one key comparison and stop the loop. And if the key is at index 1, then the algorithm will make two key comparisons and stop the loop. And finally, if the key is at the end of the array at index n-1 or not in the array, then the algorithm will make one key comparison in every iteration. And this shows that the efficiency of the algorithm is not every case, but on the contrary has cases. So what are these cases? Let Cn be number of comparisons Ai equal to k. Now for the best case analysis, we need to find the minimum number of times the key comparison is executed. And this occurs when the first element in the array is the key. I mean if A0 is equal to k. In this case, the algorithm will make only one key comparison and stop the loop. So Cn for the best case is equal to one key comparison. And for the worst case analysis, the maximum number of times the key comparison is executed occurs when key is at the end of the array at index n-1. I mean if an-1 is equal to k, or if the key is not found in the array. In this case, the algorithm will make one key comparison for each iteration of the for loop. And this can be mathematically represented as a summation of 1 that goes from 0 to n-1. In the summation, if 1 is added from 0 to n-1, that means it is added n times. And this is equal to n. So therefore, Cn for the worst case is equal to n, which belongs to big theta of n. For the average case analysis, to find the efficiency, you need to go over all cases, including the best and worst cases. And for each case, you count how many comparisons are there. And once you finish from counting number of comparisons for each case, compute the expected value of these cases, assuming that each case is equally likely to occur. To clearly understand how to do that for the sequential search algorithm, let me give you an example from probability and statistic as a motivated and related example on how to compute the best case efficiency of algorithms. In probabilities and statistics, you can view the problem as an experiment. All outcomes or results that come out from this experiment are considered elements of the sample space. So the sample space is defined as a set that contains all outcomes of an experiment. In this example, we will define the sample space as S that contains the elements S1, S2, Sn as outcomes, where n is the number of elements in the sample space S. Our experiment in this example is throwing 3 coins. Each coin either shows a head denoted by H or a tail denoted by T. Since we have 3 coins, each shows either head or tail, then we have in total 2 to the power 3 outcomes, which is equal to 8. The first outcome is 3 heads, the second outcome 2 heads, 1 tail, the third outcome 1 head, 1 tail and 1 head, and so on for the last outcome 3 tails. These outcomes will be the sample space for the experiment of throwing 3 coins. In the experiment, we will assume that all coins are not biased. I mean, when they are thrown multiple times, they are fair so that they do not favor one side over the other. Therefore, each outcome Si in the sample space is equally likely to happen. And since we have 8 outcomes, then the probability for each outcome Si to happen is equal to 1 over 8. And this is denoted by PR of Si. Now to count the number of heads for each outcome when throwing the 3 coins, we define a random variable x that works similar to a mathematical function, that if given an outcome Si, it retains the number of heads in this outcome. As an example, for 3 heads, the random variable x retains 3, and for 2 heads and 1 tail, it retains 2, and for the last outcome, 3 tails, it retains 0. To compute the expected value of the random variable x, you need to compute the sum of all products of the probability and the value of the random variable x for each element in the sample space. This is denoted by the summation of the product PR of Si, which is the probability of the outcome Si, by x of Si, which is the value of the rounding variable of the outcome Si, where n is the number of elements or outcomes in the sample space S. We can summarize the probability and the value of the rounding variable x for each element of the sample space by the following table. The first row represents the outcome Si, and we have 8 outcomes. And the second row represents the product of the probability and the value of the random variable x of the outcome Si. For the first outcome, we have 3 heads. The probability is 1 over 8 and the value of x is 3 because it has 3 heads. And for the second outcome, we have 2 heads and 1 tail. The probability is again 1 over 8 and the value of x is equal to 2 because it has 2 heads, and so on for the rest of the outcomes. So the expected value of the rounding variable x, denoted by mu of x, is equal to the summation of all the values in the table, which can be simplified by adding all values of x multiplied by 1 over 8 because it is common between all products, which is equal to 1.5. So the expected value is to get 1.5 heads, that is between 1 head and 2 heads. Finally, notice that all possible values of the rounding variable x are 0, 1, 2, and 3. So the probability for x equal to 0 is equal to 1 over 8 because we have only one element in the sample space that does not have a head, that is 3 tails. And the probability for x equal to 1 is equal to 3 over 8 because we have 3 elements in the sample space with one head. And the probability for x equal to 2 is equal to 3 over 8 because we have 3 elements in the sample space with 2 heads. And finally, the probability for x equal to 3 is equal to 1 over 8 because we have only one element in the sample space with 3 heads. These probabilities form the distribution of the random variable x. How similar are the steps in this example to the steps for finding the average case time complexity of an algorithm? The answer is exactly the same steps. I mean, to find the average case efficiency, just follow these steps but define the random variable on the number of executions of the basic operation. Let us go over these steps in detail. To do the average case analysis, the first step is to determine how many different cases do you have in your algorithm for all possible input. These cases will be used as the sample space of the time complexity. You may derive these cases similar to the way that you have derived the best and worst cases. The second step is to determine how long the algorithm will run for each of these cases. I mean, the number of times the basic operation is executed. The third step is to determine the probability for each case, assuming that each case is equally likely to happen. For example, if we have m cases, then each case will have a probability of 1 over m. The fourth step is computing the average case time complexity by using the formula of the expected value. That is, for each case I from 1 to m, multiply pi, the probability of case I, by ti, which is the number of times the basic operation is executed in case I. After that, the time complexity Cn is equal to the sum of all of these products, where n is the problem input size and m is the number of cases. Let us follow these steps to find the average case time complexity of the sequential search. To do the average case analysis for the sequential search algorithm, first we need to determine the number of different cases of all possible input of the algorithm. We have already found 2 cases, the best and worst cases. In the best case analysis, the algorithm makes one comparison, and this happens when the key is at the beginning of the array at index 0. And for the worst case analysis, the algorithm makes n comparisons, and this happens if the key is at the end of the array at index n-1, or if the key is not found in the array. So how to find the other cases? Notice that for the best and worst cases, we were considering the location of the key. I mean, if the key is at index 0, then the algorithm makes the minimum number of comparisons, and when the key is at the end of the array at index n-1, the algorithm makes the maximum number of comparisons. So the other cases should be between these two cases. I mean, we can ask ourselves, if the key is at index 1, then how many comparisons the algorithm will make? And if the key is at index 2, how many comparisons the algorithm will make, and so on until the end of the array. So if the key is in the array, we have n possible locations for the key, starting from index 0 up to index n-1. And if the key is not in the array, we have only one case. So in total, we have n plus 1 cases, n cases if the key is in the array, and one case if the key is not in the array. And for each case, you need to count how many comparisons are there executed by the algorithm. Since it is possible that the key is in the array and also possible not in the array, we need to assign a probability p for the key if it is in the array, and 1 minus p if the key is not in the array. So let p be the probability the key is in the array, and 1 minus p will be the probability if the key is not in the array, where the value of p is between 0 and 1, including 0 and 1. If the value of p is equal to 1, then 100% the key is in the array, and if p is equal to 0, then it is not in the array. So what if the value of p is between 0 and 1? For example, suppose p is equal to 0.7, then 70% chance the key is in the array, and 30% chance the key is not in the array. We will base our analysis on the probability p. I mean, if each case is equally likely to happen, if the key is in the array with the probability p, then each case of the n cases will have a probability p over n. We distribute the probability over the n cases. And if the key is not in the array, then the probability will be 1 minus p. So let us list all cases in a table showing the probability and the number of comparisons for each case. In the table, in the first column, we specify the case. In the second column, we specify when this case is happening. And for the third column, we will write the probability for this case. And in the last column, we specify the number of comparisons the algorithm is making in this case. We will start with the best case, and this will be the first case. This happens when the key is equal to A0, that means it is at the beginning of the array. And the probability for this case will be p over n, and the number of comparisons is equal to 1. Now for the second case, this happens when the key is at index 1. And the probability will be p over n, and the number of comparisons is equal to 2. And this continues for n cases. And the last case happens if the key is at the end of the array at index n-1, and the probability is p over n. The number of comparisons if the key is at the end is equal to n. So here we have the best case, and here we have the worst case. And now we need to consider if the key is not in the array. This will be case n plus 1, and this happens if the key k is not in the array A. And the probability for this to happen is 1 minus p, and the number of comparisons is equal to n. To find the time complexity for the average case, we will apply the formula for the expected value of these cases. The formula is C average of n is equal summation for the number of cases from 1 up to m. We multiply the probability for case I by the number of comparisons for case I. The number of cases we have n plus 1. So let us write the product for pi and ti for each case. This will be equal to p over n multiplied by 1 plus p over n multiplied by 2 until the last case p over n multiplied by n. In these cases when the key is in the array, plus the case that the key is not in the array. And this is equal to the probability 1 minus p multiplied by the number of comparisons, which is equal to n. We will take p over n common, and here we will have 1 plus 2 plus up to n plus 1 minus p multiplied by n. This is equal to p over n summation I goes from 1 up to n of I plus 1 minus p multiplied by n. This is equal to p over n times n plus 1 over 2 for the arithmetic sequence plus 1 minus p multiplied by n. N will go with n, and at the end we will have p multiplied by n plus 1 over 2 plus 1 minus p multiplied by n. So if the value of p is equal to 1, so here we write if p is equal to 1, then we have a successful search. So we write successful search. And in this case, the complexity for the average case for the sequential search will be equal to n plus 1 over 2. Because if p is equal to 1, this term will be equal to n plus 1 over 2, and this term will be equal to 0. And if p is equal to 0, then the search is unsuccessful. So we have unsuccessful search. And in this case, the time complexity for the average case for the sequential search will be equal to n. Because if n is equal to 0, this part will be equal to 0, and this part will be equal to 1 minus 0, which is 1, multiplied by n is equal to n. In both of these cases, time complexity for the average case for the sequential search belongs to big theta of n, which is linear. In the previous discussion for the average case analysis for the sequential search algorithm, we based our analysis on whether the search was successful if the key was found in the array, or not successful if the key was not found in the array. As another approach to the analysis, we changed the algorithm by appending the search key to the end of the array, specifically at index n. In this case, if the key is not found at indices from 0 to n minus 1, it will be found at the end of the array, and the algorithm stops the loop. This change will simplify the analysis by assuming that we have n plus 1 cases. All are equally likely to happen with a probability of 1 over n plus 1. Let us first write the algorithm with this change, then we do the analysis. So we write the algorithm header, we say algorithm, the name will be sequential search, with two input parameters, the array and the key element that is labeled by k. We will use a while loop that will iterate over all elements of the array using a variable I. So the first value of I will be 0, pointing at index 0, and we append the key to the end of the array. So the last index for the array is n minus 1, and at the end of the array will be at index n. So we write an takes the value of k. In the while loop, for the condition, we will not test the value of I if it has reached the size of the array or not, because the search is always successful. So basically, we will search for the key. So we will say while ai is not equal the key, go to the next element. Eventually, the value of ai will be equal to k. So how to check if the search is successful? After exiting the while loop, we test the value of I. If it is less than the size of the array, then the search is successful and it is found at index I. So we say return the value of I. Otherwise, it returns -1, indicating that the key is not found in the array. In this algorithm, the search is always successful with n+1 cases that the key is in the array. In cases if the key is found at index 0 to n-1, and one case if the loop reaches the end and found the appended key. So there is one comparison of the keys at index 0, two comparisons if it is at index 1, and so on, n comparisons if it is at index n-1. And finally, for the last case, there are n+1 comparisons if the key is equal to the appended key. If we assume that all cases are equally likely to happen, given a probability of 1 over n+1, we can write the time complexity for the average case as follows. We write C, the average case of n, is equal to 1 over n+1 multiplied by 1 plus 2 plus 3 up to the value of n if the key is found at indices 0 to n, plus the last case if the loop reaches the end and found the appended key, and this requires n+1 comparisons. This will be equal to 1 over n+1 times the summation that goes from 1 up to n+1 for the value of I, and this is an arithmetic sequence, and this will be equal to 1 over n+1 times n+1 times n plus 2 over 2, and n+1 will go with n+1, and this will be equal to n plus 2 over 2, which belongs to big theta of n, which is the same result we have obtained in the previous analysis.